So we talked about Moore machines and Mealy machines based on the outputs. In a Mealy machine, a Mealy state graph, the output at any state is defined by the state and an input at the input. So in a given state there can be more than one output because there are more than one input possibility. On the other hand, a Moore machine, the output is tied to a state. A particular state will have only a particular output, and the output will change only when the machine changes from that state to another state. For example, if a machine is in state S0 and there is an input variable called x, so in state S0, if x is 0, the output can be 0. If x is 1, the output can be 1. On the other hand, the Mealy machine will say, Moore machine will say at S0 state, S0 the output is 0. The output has to change, it has to go to another state. So we will do some more machines, drawing of the state graphs. As I said, that is the most important step. The reason I want to spend a little extra time on this is the most important design step. If you have understood the problem very clearly, if the problem has been stated clearly to you by the user, the client, and you are the designer, first of course you have to understand the problem clearly. Of course that person has to state the problem clearly to you, but ask all questions to understand that there is no ambiguity, there is no uncertainty. Having said that, you will have to, first step is to draw the state graph. Once you have the state graph, the rest will fall in place. That is why I thought it is important, and the designer's job is to get a best state graph possible for a given set of specifications. From then on to the rest of the design procedure is simple, because it is a standard procedure. Anything which is standard can be simplified and also even automated. Today, the age of computers and automatic design, computer aided design they call it, CAD, or they call it EDA, electronic design automation. These are all the industry terminology for automatic design. But all that will come only after you have gotten your state graph. Of course, the state graph also the computer can generate, but then it may be suboptimum. The designer's creativity, designer's innovation, the designer's specialization can be shown only at this stage of drawing a good state graph. That is why I thought I will spend some extra time and give you one or two more examples. So let us take another example of course we will also do systems later on. There also we will have to start with state graphs, but here at this point in time in our course, since we are talking about state graphs, just taking a state graphs example without any sort of overall system view, I will just define a system with an input and output and the conditions under which the output has to be there, and then we will have to draw the state graph. So let us take an example of a Mealy state graph. For a circuit with one input x, with a serial input x, and an output z, that means with every clock pulse at the edge of the clock, a new input bit is sent into the hardware. That means there is an input which comes, it can be same also, it is sampled during every clock transition. The input is sampled at every clock transition. The value has changed, it will take the new value. If the value is not changed, it will still take the value as a old value. So it will be a series of ones and zeros. And then we want an output z, also is a series of ones and zeros, and then the relationship between x and z will be the following. Whenever there is a pattern we did the pattern generator, Z should be 1 coinciding with the last bit of the pattern (1 0 0 1) or 0 1 0. Either this or that happens. So if the input with as a pattern 1 0 0 1 along with the fourth one, output will be 0 0 0 1 here. Similarly, the input is 1 0 1 0 1 0, the pattern of 0 1 0 is detected by the circuit, and output Z should be 1 correspond this 0 during that clock period. Rest of time the output is 0. 0 otherwise. So we will also assume there is overlapping is allowed. Overlapping of the two patterns or the same pattern repeated also has to be considered as completion of the pattern. Overlapping of patterns also should be considered as so that means there is a series of bits 0 1 1 0 0 0 1 0 0 1 0 1 0 1 1 0 0 like that goes on. Sample input and output. Sample input and output sequences. So we are looking for this pattern 1 0 0 1. Here is there, or 0 1 0. That's a 0 1 0 here, right? That is a 0 1 0 here, 0 1 0 here. Right? So Z should be 0 0 0 0 0 0 0 1 0 1 1 0 1 0. This one is for completion of this 0 1 0. This one is for completion of 1 0 0 1. This one is for completion of 0 1 0. This one is for completion of this 0 1 0. Similar example similar to what we did the last lecture, but slightly more involved in the sense there are two patterns. One is a larger pattern and then this overlapping is also. So we wanted a Mealy machine, that means each arrow from each state we will have to look at the possibility of x being 1 and x being 0. We have to decide the next state and the output for each of those. So let us start with always a 0 state or a reset state, call it S0. The input is a 0. It could be the first form. If an input is 0, output is 0, so x and z. Output is 0. Go to state S1. So S1 state is a state where 0, pattern 0 has been identified. If it's a 1, another state x is 1, z is 0, output is 0. This state 1 would have been registered or memorized or recognized, whatever you want to call it. Then in S1 again it can be 0 or a 1. If it's a 0, it could be, it's not going to give you any extra information, so it could be start of the same new sequence to 0. On the other hand, if it's a 1, we'll go to S3 because we have now identified a 1, 0 followed by a 1, which could be the first 2 bits of a 0, 1, 0 pattern. Likewise in S2, if 1 comes, it could be the beginning of a new pattern, so no extra output. It continues to be the same state. If a 0 occurs, on the other hand, it will be 1, 0, could be the first 2 bits of a 1, 0, 0, 1 pattern. Because we want to detect both of these, 1, 0, 0, 1 and 0, 1, 0. So if the 0 occurs, let us create a new state called S4, in which 1, 0 will be remembered. That means up to this point a pattern of 1, 0 has occurred. That's what it means. So you have to proceed like this for each state, and then until you have finished your patterns and no more possibility is there. So in S3, 0, 1, if a 0 occurs, 0, 1, 0, pattern is completed, and that could be also part of 1, 0. 0, 1, 0 could be the first 2 bits of a 1, 0, 0, 1 pattern, which is already here, S4. So if a 0 occurs here, go to S4, which is 1, 0, but it will produce an output of 1 in this case because we had completed as pattern 0, 1, 0. X is 0, leading it to a 1, 0 state, and a new one, and the 1 is the output because 0, 1, 0 is now completed with this 0. On the other hand, if the 1 occurs here, it is a 0, 1, S3 0, 1, 0, 1, 0, 0, 1, 1. 0, 1, 1 has no meaning. The only one, the last bit 1 is the of any value. So that is in this state, S2. So if the 1 occurs, so we exhausted S3 and also finished the pattern 0, 1, 0. So let us continue with S4 and see how to complete the pattern 1, 0, 0, 1. S4 is 1, 0. So if a 0 occurs here, that will be a part of 1, 0, 0, 1. So I will have to create a new state for that. S4 with a 0. We will go to a new state called S5, which will remember 1, 0, 0. No output again, because 1, 0, 0, 1, only when that is completed we will have an output of 1. When 1 occurs in S4, S4 is what? 1, 0, 1, 1, 0. So if 1 occurs, is a 1, 0, 1, it could be the first two bits of a 0, 1, 0. Correct? So if 1 occurs in S4, it can go to 0, 1, which is S3. Correct? So S3, this is 1 occurs. Now S5, if S5 is 0 occurs, then it's 1, 0, 0, 0. So 1, 0, 0, 0 has no value except that the only 1, 0, the last one 0 is any value, which is S1. So if the 0 occurs, On the other hand, if 1 0 0 1, if the 1 occurs here, the pattern is completed, and the last one 0 1 of that 1 0 0 1 could be the part of the pattern 0 1 0. So S3 is that 1 0 0 1 S3. So I'll have to go here to 0 with an output of 1 because it has completed just now the sequence of 1 0 0 1. One is the input, 1 is output. Lot of, you see, of course, from here you'll have to go to the state graph, state table, and all that. We'll talk about it a little bit. We'll talk a little bit about it. But one thing I want to say here is, the problem is simple, 2 patterns, and you can mentally sort of visualize the whole thing, but the problem becomes more complex. This is not a pattern detector, some other problem, or even a pattern detector, longer pattern, or more than 2 patterns. You will lose track of some of the combinations which has already been there. Of course, we take notes here. So do not worry about creating an extra state. Any design, that is the rule, thumb rule of any design is, don't worry about extra hardware to start with. Start with to make sure that all requirements are taken care of, all specifications are covered completely. You can have hardware which is redundant. Of course, it is not efficient in terms of speed, cost, power, but that is better than having a hardware which will not work properly, which is inaccurate, which will give an erroneous behavior. So when in doubt, create a new state. If supposing you are in a particular state like S4 and then 0 occurs, whether it should go to another existing states or should create a new state, of course, if it is a very simple thing like that, you can always think for a minute and visualize it and go there. But in case it's not possible, the diagram becomes longer, bigger, and you are not able to really take all the possibilities into account, you can as well create a new state and proceed. So you may end up with more than the minimum number of states. That is not a serious difficulty, even though more states means more flip-flops, and more flip-flops mean more driving logic means more hardware, takes more space, costs more money, consumes more power. All that is fine, but its system will still work because you are taking care of all specifications. So do not be over worried about simplifying. Of course, it doesn't mean to say that you should design inefficient circuits all the time, but when in doubt, create a new state. But of course, later on, of course, there are techniques also to make sure whether this is indeed the simplest possible state graph. Any extra states can be knocked off by a process similar to this Karnaugh map. There, the Boolean algebra, we went through the Boolean algebra, reduction of the terms, reducing the term to a minimum using Karnaugh maps. Similar concept is also possible in state reduction. So once you have a state graph, I can reduce the state graph to the minimum possible number. A state graph is the minimum possible number of states. I don't intend doing that now at this stage. If possible, if there's time left, we'll probably do that part a little bit by a couple of examples maybe. I can show you how a state graph with more states than required can be reduced to a state graph with a minimum number of states. There's a technique for that. So since the technique is available, even if it is not available, I would rather go with a conservative state graph which will take care of all my possibilities, rather than going and I will draw a simpler graph and then ignore some of the possibilities. But in these two options, I will any day prefer the option in which I will have more states, but I can solve the problem to the entire specifications. That is one point I wanted to make here. State reduction to minimum number of states, that's the technique of doing it. Some textbooks will talk about it. I think many textbooks nowadays talk about it. If possible, we'll cover it, even though I don't want to do it at this stage. The next thing is the number of, once you have number of states, what do you proceed with? How do you proceed? You have to assign the states. Now, there are 6 states, 0 to 5, there are 6 states. 6 states is the minimum of 3 flip-flops are required. So you can start, you can call these variables A, B, C or P, Q, R, whatever, and then start giving 0, 0, 0, 0, 0, 1, that is a arbitrary assignment. This is called assignment. Once you have a state graph with states symbols rather than binary values, converting the state from symbols and letters into binary variables is called a state assignment. So one is reduction of states, reduction of state graph. These are the steps you need to do. Which I said I am skipping at this point in time. Second is the state assignment. State assignment is a process of mapping or assigning binary values to the states. I cannot start with 0, 0, 0, 0, 0 1 because I never know when I start the problem how many states are going to be total. So how many binary variables I should get started with, I don't know. Otherwise I would have started with 0, 0, 0 here, and then I will go to 0, 0, 0 state will go to 0, 0, 1 state, 0, 0, 1 state will go to 0, 1, 0 state. I can make a map, I can make a graph like that, but I don't know because I don't know how many variables I should start using. So I would probably start with symbols, and then later on, after finding out how many states are required, I will assign it. Now I know how many state variables are required. Now I know that 3 state variables are required. So I am going to call them P, Q, R, whatever. So I will say S0 is making this assumption, assignment, etc. This is called a state assignment. This process, this step of converting the symbols, state symbols into binary values, state assignment. Here again I can do a little more efficient. This is an arbitrary assignment, natural binary sequence I have taken and assigned it. It is always possible, you see, finally the state values become the present state values, and then the next state value depending on the state graph, and then from there you go to the flip-flop inputs and the outputs. So the corner map is drawn based on the transition from the present state to the next state, is it not? The simplification of the hardware finally, the hardware that we are going to finally get, the steering logic we are going to get, depends on the present state and the corresponding next states. So if from S0 is the present state and S1 is the next state, what is the best possible assignment of S0 and S1 so that a minimum hardware is required for transition? This is also a problem of interest in reduction hardware. So there is a possibility of optimally assigning the binary values to the states rather than randomly or arbitrarily assigning as we did in this case. Can I make a more efficient assignment? Hardware efficient assignment. By this what I mean is, instead of blindly saying S0 is 0, 0, 0, S1 is 0, 0, 1, S2 is 0, 1, 0, instead of saying that, can I use some sort of a rule and figure out which state should be next to which state? This is called neighboring states, or the, whenever a state variable, the state assignment of one state differs from another state in only one variable. These are called adjacent states. 0, 0, 0 and 0, 0, 1 are adjacent states, like the corner map, right? In corner map, adjacent cells differ only in one variable. Like that in binary assignment also, adjacent states are the states which differ only one value of the state variable. Other state variables are same. So use some adjacency rules. Using this is also possible. These are steps to reduce the hardware. This will reduce the hardware because less number of. So this is very important when it becomes, for example, from 9 states, if I am able to reduce to 8 states. It's a significant reduction because instead of 4 flip-flops, I can use 3 flip-flops. State reduction becomes more meaningful if I can reduce the number of flip-flops. Even otherwise it will make meaningful, because if I have less states, instead of 6 states, if I have 4 states, even though in both cases I will use 3 flip-flops, I will have more don't care values. The number of states is less. When I have more don't care values, my hardware is simpler, you know that. When I have more don't care entries in my state table, my hardware is simpler. So to that extent it will also impact the hardware, but it's more significant reduction is possible if you can even reduce the number of flip-flops. The same argument I can hold here. If you have an assignment state such that the transition always happens from one state to the next state, which is differing only one variable, the switching activity or the transition is minimum, that is also efficient. Again I am going to skip this part of the thing right this point. These are I want to tell you, these are the things which are possible, it can be done and should be done for efficient design, but we will have to first go through the design procedure and then later on if we have time we will do it. Why am I not giving a lot of importance to these at this point in time is because today, in today's technology, nobody bothers with hardware cost. Because gone are the days where you have to count the number of gates. If you can do something with 7 gates instead of 6 gates, 7 gates instead of 9 gates, 7 gates instead of 8 gates, we are very happy. I reduced 1 NAND gate. Today, as I said, these ICs, integrated circuits, which have a large number of gates inside. On one single chip, I can have a gate equivalent function. Even though we call it gates, it's not that 1000 gates IC, it does not mean that 1000 gates will be sitting there. There are functional parts, functional blocks within that IC, which are capable of delivering the performance of about 1000 gates. So what is the point in having a gate like that, performance like that, and 1000 gate, and then reducing it from 767 to 734? You can only say I have made a less. Of course, a little bit increase is there in the term of switching activity is less. To that extent, there is a power saving, but the size is the same. The IC is there, sitting in your board. There is some marginal advantage. Anyway, there is always a marginal advantage, but the amount of advantage in terms of cost and the size and even the power consumption is not as significant as the earlier days where each one is a separate IC. I have to buy and put an IC. One AND gate means one extra thing I have to put. One multiplexer I need to put one extra thing. One flip-flop I need to put an extra. For each one I have to go and buy an IC and put it there. It takes more space, more power, more money, more everything. Speed is reduced. So those days hardware reduction was very significant. Today we are having, thanks to the technology advancement, so-called VLSI technology, advances in VLSI technology, it's so common that everybody talks of VLSI even without understanding what it is. People talk of VLSI. You have newspapers which talk about VLSI courses. So because of that, this hardware is available in plenty. It is not very important unless it's a critical issue. For example, if I have 1000 gate solution, nearly 1000 gate solution, it is slightly exceeding 1000 gates. I will try to accommodate in a 1000 gate solution, other than the next possibility is 2000 gates. I would rather do some exercise to reduce it to less than 1000 so that I can use a smaller IC than a 2000 gate IC. So certain critical areas are certain speed issues when it comes to high speed applications. Today the technology, both speed wise and hardware availability wise, there's plenty. We don't have to worry about the speeds of normal applications except in very high speed applications, high speed computing. Likewise, hardware availability is enormous. Cost saving is minimal, if at all there is any. Because of these things only we are skipping these steps now. There is no point in doing it. But at the same time, as a designer, if you want a digital designer, you should know that it's available here. When you need it, you should be able to apply it. You may be an IC designer. Later on, you may be doing a very sophisticated IC in which every critical component is critical in the sense of area and space and everything. So you have to go and optimize, start optimizing block by block. You should know what are the techniques available to you for that. So I don't want to sort of not let you know that there are things like this which should be done, which could be done. But it is not important, especially in a small systems like this. Talking about a pattern generator with 3 flip-flops we are talking about here, and a bunch of gates, the whole thing is over, which can accommodate one small integrated circuit, the medium scale IC, MSI. The whole design is one MSI. I buy an MSI and put it there and it works. So why bother about trying to do some of these things? That is the reason I'm skipping some of these steps now at this point. So we will do an arbitrary assignment most of the time until we have time to go revisit these areas, try to do some of these things if possible. So we will do a normal assignment. From here you know how to do it. That means I have to do a state table, which can be also considered as a transition table depending on the type of flip-flops. So I have to say present state, input, next state, output. Present state values are, what did I say was PQR, ABC, whatever. PQR, next state values. Let us use D flip-flop so that PQR are same as DA, DAB, DP, DQ, DR. For other types of flip-flops, I should have separate thing. So this then gets state table is also a transition table. Output C. So we'll have 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. The last state is 1, 0, 1. X is 0, what happens? X is 1, what happens? And then other two states are not being used. These are all don't cares. Remember, in the don't care also the output should be what? Zeros. So you can complete this table. You know how to do that. From here, this is 0, 0, 0, this is 0, 0, 1. So 0, 0, 0, so I will write one entry. 0, 0, 0, x is 0. It goes to 0, 0, 1. Output is 0. 0, 0, 0, input is 1. It goes to 0, 1, 0. Like that. Please fill this and design the circuit using D flip-flops and gates, simple as possible. That is an exercise, you can do it yourself. We have done enough of those by now. So this is how you start from a basic problem definition with very clearly stated specs. Take all possibilities into account, draw the state graph. From the state graph, you do the state assignment, reduce the state if necessary and if possible, reduce the number of states. Do a state assignment either randomly or arbitrarily or using some thumb rules or design rules to make it efficient. From there you go to the state table and decide on the type of flip-flops. If the flip-flops are other than D type, you draw a transition table which is other than the state table. From there you draw the corner maps and simplify and then draw the gates, circuit steering logic using gates and the flip-flops which will be driven by this steering logic. And then your circuit is over. Then you start giving the patterns and then test it, build it and test it whether it works. Because this is only a sample sequence. You don't have to give the sample sequence. You should give any sequence. Whenever any sequence you give, this pattern is identified, it should be immediately given output of 1. Do you have any questions? This is a total procedure with a slightly involved, I won't say it's a very complicated problem, but slightly involved compared to what we did in the last lecture. We will do one more example of the state graph generation, this time using Moore machine. We have not used that so far. We have done only Mealy. So let us do a Moore machine state graph. Rest of the thing is easy. Once we have a state graph, you know state assignment. I am not going to talk about all these things one more time. We will have a state graph, then from there you know the reduction if necessary. Then you go to the state assignment, either arbitrary or efficient assignment, and then this logic design using hardware. So let us, maybe we will use the same problem and instead only change this to Moore. And also this time we will not identify overlapping patterns. I will give you two variations. That means I should clearly have a 1001, output will be 1, that 01 will not be considered as a part of another sequence. Again it has to start with a 0010. Only then it can be a returns pattern. So non-overlapping. So I am going to reduce this. Overlapping of the patterns need not be. Design a Moore machine for the same patterns and do not have to worry about overlapping. You will always assume that our pattern is completed, it starts all over again. That means you have to go to the reset state. After every output 1, you have to go to the reset state, start all over again. That is what it means by non-overlapping. Is it not? You start with the reset state, the pattern is completed. Since no overlap is allowed, you have to start with the reset state and again wait for the next pattern to come. Is the problem clear? So now if you want to use the same sequence, I don't know, as an example, now 1001 is identified here, but the 010 I will not recognize as a part of a pattern because it is a non-overlapping. So this 1001 will produce an output of 1. Until then the output will be 0. Okay, you are right. I didn't see that. Thank you very much. What was that again? Right? You put it like this? Huh? 010, right? Yeah, I know. That's what I am saying now. So you have an output here because of this pattern. Now this 1001 gets knocked off. So let me put it to give an effect of. Then this 010 also will be identified since it's a separate pattern, non-overlapping. It's only a sample sequence, it can be anything. And then 1001. The type of input output we want. We have two variations in the problem I have made. One is that we have Moore machine, not a Mealy machine. That means the output will be decided in the state and not as along with the arrows. The second thing is there will always be reset after pattern is detected and then start all over again. You will have to quickly draw the state graph and rest of the things you will do it yourself as homework. Complete this also, is also homework. So let us start with S0, the reset state. Zero. Now I don't have to draw arrow this. I have to draw the output within this state. So usually you put S0, that means in this S0 state the output is 0. That's what it means. Along the arrow we draw the inputs, we will mark the input. Inside the state you mark the output. So when you go to S1, S1 is a 0 state, remember. 1, S2, 1 state, remembers. Now here it can be a 0 or a 1. If it is a 0, it will continue to be in the state, correct? As long as any number of zeros is there, we have S1, assuming the letter 1 is the only 0, letter 0 is the only 0. Then, so 1, it will go to this, S3 is a 0, 1 state, 0, 1 state. Then in S2, if a 1 occurs, continue to be here. So 0 occurs, it will be 1, 0, which is again new. Then you are in S3, output is 0, 1, it is 0, 1. So 0 occurs, pattern is complete. Do you have a question there? Yes.
With this 0, can you go to S1?
Which 0?
S2 from S2 to 0.
S2 to 0.
Can you go to S1? Because it can be a new pattern of 0, 1, 0 starting off.
1, 0. It will be a 1, 0. Why 0, 1, 0?
So S2 is the pattern is 1, 0, 0, 1. If S2 proceeds,
S2 proceed to?
continues to go, you get the pattern of 1, 0, 0, 1.
Yeah.
But it can even be the pattern of 0, 1, 0 just proceeding there.
0, 1, 0, where? We have 1 already here, 1. Here there is a 1. Since already is a 1 here, we are here only if it is a 1 has occurred. If it is a fresh 0, it would have been here, no? Oh, you mean this could be a new start?
Yeah.
This could be a old 1001 or starting of a new pattern here. It can either go here or here, you are saying. I think we'll do this, stick to this, because we will have 2 patterns to detect first. We will consider that little later on separately. I think it will not, from here a 0 occurs. I would rather like to use it as a pattern, 1, 0, 0. If it is not going to result in a pattern, then you are losing that extra 0, that's what you are saying. Yes, you have.
We can have a arrow going from S4 to S3 if a 1 appears after the 0.
That we are going to do anyway now.
So that will take care of.
Yeah, S4 to S3 we are going to do it now. Let us complete this. Now in S3 if it is 0 occurs, what will happen? 0, 1, 0 completed, correct? It will go to S5. I cannot go into any other thing because S5 1, because output has to be 1 here. A new state in which output has to be 1, I cannot go to one of the states which is already there because all those states are only zeros. So this is a 0, 0 state, that is S5, 0, 1, 0. So 1 occurring here, this is a 0, 1 state, this is no meaning, this has to go here. 1 occurring, 1 occurring here will go here. Let us look at S4 now. In S4 if a 0 occurs, it will go to S1 now, because it is a 0, 1, 0, 0, this 0, 1, 0, oh, if a 0 occurs, it will go to S6, 0, so 1 occurs, it will go to S2, S3. This is 1 0 1. 1 0 1 would be the 0 1. Okay. So that is what that 0 you are worried about, that has been now taken care of. This 0 would not have been lost now. You don't have to return it there because you would anyway go to the S3. So this is a 0, now S3. This is when? So 1. So you consider both arrows here. Now this is what? S6 is 1 0 0. S6 is 1 0 0. Now in S6, if a 0 occurs, it will be the start of a, there is no use because 1 0 0 0 has no meaning except the last 0. If on the other hand, if in S6 1 occurs, the pattern will be completed, the output will be 1. So if S6 1 occurs, we will go to S5, make an output of 1. Since there is already an output state with an output of 1, we will put this output here. That means S5 is a state where we will have output 0 1 0. I mean, remember 0 1 0 as well as 1 0 0 1, with both as an output of 1. If on the other hand, as I said, if 0 occurs, this 0 has no meaning. It could be only, it could only be a start of a new sequence after resetting. A new sequence 0 1 0, and that is where S1 comes into picture because S1 remembers as 0. So if 0 occurs, it goes here. S5 is a state where an output is 1. That means we have completed a sequence either 0 1 0 or 1 0 0 1. Whether a 0 or 1 occurs, it should only be a start of a new sequence. If a 0 occurs, it will go to this S1 because that is the start of a new sequence with a 0 for 0 1 0. And if 1 occurs, it will go to S2 because that is the starting point of a new sequence 1 0 0 1. So 1 will take it to this new state, S2 state, which starts a new pattern with a 1 start for 1 0 0 1. If 0 occurs, it takes us to state S1, which is the start of a new sequence 0 1 0 here. Now the diagram is completed. It's 6 states plus 1, 7 states totally. Again, you use 3 flip-flops. You can draw the state graph with the present state values arbitrarily assigned as 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0, and then the input x is equal to 0. What is the next state? What is the output? Of course, output is dependent on the state now. So the input x is equal to 0. What is the next state? Input x is equal to 1. What is the next state? Then for each of the present state, you write the output. That becomes the state table. And depending on the type of flip-flop, you can do the transition table and finish the hardware. So I leave the rest of the problem as an exercise to you. Complete the draw the state graph from here, and using the flip-flops, get the corner maps for the next state variables as well as the output, and then draw the logic diagram of this. With this, we will complete the state graph drawing as an exercise. But of course, we will visit this area again. When you do the system design, naturally again state graph will become part of the system design. Also, if time permits, as I mentioned earlier, we will talk about some simplification procedure for reducing the number of states and also for hardware efficient assignments. We will continue with more concepts in system design from next lecture.